Yes,
Yes, sir.
Mr.
Yeah. So good afternoon. Today I am going to talk about challenges in archival and analysis of planetary samples. So I'll try to connect these to whatever we are doing, and then to what are the difficulty or how we are doing. I'll try to connect. So as we know, the solar system formed 4.6 billion years ago, and still the origin and evolution of solar system is not completely understood. So this can be understood by studying the geochemical properties or the isotopic properties of the solar objects like asteroid, planets, and their satellite. Though we have Earth sample, which is a part of solar system, but we need to understand the early evolution. Especially, we need pristine sample. But in Earth, because of the recycling and the volcanic activity and the metamorphism and the alteration products, all these things, the rocks have been changed time to time. So the oldest rock which represent to the solar system formation or near to the solar system formation is rare. So we have to depend on the samples from like meteorite and the return sample. So meteorite can be from either from asteroid or any planet like Moon, Mars, etc. So just this is to show you how our solar system has formed. So basically, our solar system formed from a dense molecular cloud. The molecular cloud basically consists of gas molecules, mainly the hydrogen, helium, dust, water or moisture, and few other heavier molecules. Because these are have large size, they are gravitationally unstable, and because of that they try to collapse. Because of this collapse, the kinetic energy increases, and there is a high angular momentum, and they form the disk and a high mass concentrated in the center, which correspondingly is from the your protostar, which is the young sun, and around that the accretion disk. Subsequently, the nearby sun area, the due to the high temperature, the particles start dust particles when the heat is releasing. The dust particle, tiny dust particle are forming, and when again the radiation due to the radiation, the near to that sun, the condensation starts and the dust molecules accreted and form the subsequent objects like CI, control, planetesimal, and later on you can see the present status of solar system forms. This is just to see is a microscopic scale. If you can see inside the disk also, you can see a lot of things inside the disk. So we can see inside the disk there are these are the dust particles, and subsequently we can see the outer, there is a icy planets and the rocky planets are forming near to the sun. So if we again see that near to the in the hotter region, as I told, when the heat is transferring or the heat is going down, the refractory elements are forming first. So which is called as the calcium aluminum inclusion, and then we are after that we are forming the chondrule and then the accretion of planets. So Ci are the first form solid in the solar system, then the chondrules forms, and subsequently the accretion of protoplanet, and then the differentiation of planet form is forming, and you are getting the what we are seeing the planets like Earth, Mars, Moon, and Venus. The CA are basically the as I told, these are the first solid form in the solar system. These are refractory in nature. That means they have survived through the high temperature and pressure, and they are formed close to the sun, and they consist of a lot of refractory minerals, and they are basically condensed from gas to solid, and the condensation temperature, their condensation temperature is given in the side table. So condensation temperature is nothing but the temperature at which the 50% of the material has been condensed. So CI basically mainly consists of the corundum, evonite, malachite, frostite, spinel, perovskite, etc. The controls are basically formed after the formation of CI, and these controls are basically found in the chondritic meteorite. And these chondritic meteorite are primitive in nature, and the controller are the basically the silicate moltens of silicates, and they are mostly consist of olivine pyroxene, the glassy material inside, and few metal and metal sulfides. So this shows the basic cartoons of how a controls. This is spherical in nature, and these are the objects related. This is the olivine. This is the pyroxene. These are the metals, and these greens are basically the glassy major certificates. This shows there are different types of controls. So these picture shows how the different types because of the where it formed and at what temperature it has formed. Depending on that, the type of formation of controls are different, and because it is forming near to the sun and from melting of dust. So the study of this type of and the control can give us the information about the history of the what type of dust and how it formed the total environment and the history of the control and the earlier stage of dust. This chart shows the how chondrite has been divided. So chondrite are mainly of three types: carbonaceous, ordinary, and insertite. Then again, carbonaceous chondrite are been divided into so many types. That is CI, CM, CO, CV, CK, CR, CH, CV. These are basically carbonaceous, means they contain carbon in their composition. Similarly, ordinary chondrite has been divided into H, L, and Ml. H is basically for the where iron is higher content, and the L is the total iron content is low. Unsaturated chondrite are basically formed in the reduction condition. Then this is R and K type. This CI and CM are basically the aqueous altered meteorite. That means they have water in their body, which has melted and altered the primary phases of silicates into secondary phases. So the CI and CR mainly contain the water, and their water content varies from 20 to 9 to 20%, and the CI composition mostly represent the composition of sun. The other type of these type CM to CV, they mostly contain control, but CA has no control. All control has been altered and from the polysilicates. So once we get or find so meteorite can be also two types. That is, one is fine and one is fall. Fall means if someone has seen or observed the meteorite is falling and that has been collected immediately, that is fall. And if a meteorite has been found long time back and someone has got it, this is fine. So generally we prefer a fall one because the weathering due to the Earth's interaction has not been carried out in the fall type meteorite. So in fine, we don't know what is the grade of fall weathering has been. So that if you are getting a fine, we have to check all these before starting our analysis. So in when you are getting a meteorite, first we have to characterize it. What type of meteorite? So for that we have to do a chemical characterization, and then later on we can do the study of isotopes. So in bulk in the composition, we can have a bulk composition, and then in phase composition. In bulk composition is generally carried out using a XRF, which is basically measure the X-ray fluorescence, characteristic X-ray fluorescence, and the abundance of the elements has been abundance of the elements has been deduced from this characteristic X-ray. So this is a destruction process. So that means we have to powder the sample and make pellet and do the measurement. So until unless we have huge amount of sample, we don't go for this type of analysis. But we like to do because that gives easy to that helps in the characterization of meteorite. Then again, we do the study of trace element and rare element study. So that is done by using a ICP-MS. ICP-MS basically we have to process the sample using chemicals, and that process has to be done in a ultra clean laboratory class 1000 or 100 class laboratory. This is also a destruction process, but for characterization, this process is needed. Then in phase chemistry, basically we this is a in situ measurement technique. So we have to prepare a thin section or thick section. Thin section generally prepared using a glass slides, or in thick section we prepare the sample by putting the resin and hardener, then do the polishing using the grind machine. So using this machine, we can measure the or identify the whatever the mineral phases present in the our sample. So in the left side, this shows a backscatter image, which basically this shows a basically altered contour, and inside that we can see the different grayscale. So the darker one is the higher silicate, and the lighter one is white towards the metal. So using this also use the same X-ray fluorescence technique, where we reduce the elemental concentration using by measuring the X-ray. This is a electron microprobe. So once we do the characterization, basically in characterization we try to see what type of meteorite, like it's a carbonaceous, ordinary, or a encephalitite, or a achondrite, or differentiated. Then after that we plan what to do. Then basically we go for what is the age. If you want to know the age of the sample, we have to go for chronology. And other type of isotope to study the different type of processes, like where it form, what is the environment, all this type of can be done using the different isotopes. So in geochronology, basically studied by using the long-lived radioactive isotopes, and where the parent decay to a daughter by the radioactive law. And few example is the rubidium, strontium, uranium, thorium, where their uranium to uranium lead, the half-life is roughly around 4 billion years. So the Using this chronology systematic, we can get the accurate age, and this type of measurement can be measured using a different type of mass spectrometer. So for isotope measurement, we have to use a mass spectrometer. Basically, mass spectrometer operate on the concept of MIE, where your M is the mass and E is the charge. And there are different type of mass spectrometers with like a secondary ionization mass spectrometer, where it dig out the secondary ions using a primary oxygen or a cesium or radioplasma, and measure the secondary ions using different type of detector. In thermalization, basically we have in TIMS in or thermalization, we have to process the sample, and then you have to do the column chemistry, where we separate the each element and then load the sample into a filament. And this filament is heated using some iron source, and then the ions are being floated to a mass analyzer and detected using a detector. The same solution type of solution can be used also in MCICBMS. And in MCICBMS, basically they used a plasma source, where the solution has been passed through a plasma or RF chamber to ionize the solution, and then we measure the isotopes. This shows different types of mass spectrometer. These two are basically operates in the principle of secondary ionization. This is the TIMS, this is MCICBMS, and this is noble gas, where you do the measurement of noble gas only. So this table shows the different systematics of where we can do the who has the long-lived radioactive half-life, and then these can be used for the geochronology purpose. SIMS use a in situ technique, so these are non-destructive, and TIMS and ICBMS are the destructive method. Okay. So similarly, there are also few elements who has very short life, have a short life, or the low half life. For example, is aluminum magnesium, where half-life is 0.7 millennia. So these type of systematic can be used to find the time of several millennial scale, which is basically used to find the reference or the relative age. So in a long-lived systematic, that is gives you the absolute age, where the short-lived radionuclides basically used for the relative scale. For example, aluminum magnesium can be used to find out the what is the heat source in the for example, when you are saying the aqueous alteration is happening in a asteroid body, so that basically is from the aluminum 26. So aluminum 26 decay to magnesium 26, where we measure the excess of magnesium to find out what is the time period where this excess of magnesium is deposited. That gives the total time period up to what the system is active and generating the heat. These are few short-lived radioactive elements which is used for different purpose. So now that earlier we saw the how different instrument has been used to either measure the concentration and isotopic study to understand different uh, purpose, like to measure, find out the mineral composition, or isotopic study to understand different processes, and the chronology or the age of the sample. This is also important to how to preserve the sample. So the main objective to for the to protect and preserve then distribute the samples, especially when we are taking the sample, return samples, they are very low amount and they can be contaminated easily, so that they have to preserve in well defined methodology. So therefore nowadays in all space mission body are basically making um, sample curation facility. So when you are saying the some sample curation facility, the samples can be of two type. One is restricted and another is non-restricted. So samples which are coming from Moon, Mars, asteroid, comets, etc., are basically non-restricted, and restricted mean we can have the habitable environment. So they may have life which can be biohazard, so that we have to be extra cautious when we are taking those type of sample. So when you are saying the curation of samples, so the sample can be from various type. One is from meteorite collection, another is a return sample from a moon, Mars, asteroid, IDPs. Also, we can have precious analog sample, which may be a natural or simulated analog sample. So, so for this facility, we need a trained manpower, clean labs of different grades, and then sample storage, and then to characterize the initial characterization within the storage system, we need some basic instrument, and also to distribute the sample, we need a whole set, suit of instrument to cut, to process, and then polish and make the sample for the measurement also. So before doing any process, we have to first make the catalog so that it can help. So where we can mention the amount of some property, like what is the mass, what is the color, any special feature in the sample or not. This type of catalog you can do, that can help while doing the characterization of sample, and it is easy to understand the physical properties of sample. Then we can provide the once you distribute the sample, we should have a log where how much sample has been distributed and what is left out. So this is just a sketch for a lab for a curation facility, how it should be. So there are different grade of clean lab you should have, where the very pristine sample can be put in ultra clean laboratory, and some sample which can be handled in atmosphere or in little bit lower grade also we should have a chamber. Also there should be some space where we can you handle the sample in open, so it should be environment friendly. All should be taken care while handling the sample. These are a few picture from NASA lab, where how they have stored the sample. These are the sample chamber where they are not touching the sample directly. These are globes where they put their hand to touch the sample. So this is another case. So these are different pictures where sample has been kept. So this is from Hayabusa sample, where the curation facility for Hayabusa. We can see different instrument also has been attached to the chamber, where FTIR, microscope, and even to touch the move the sample, there are some facility, and inside that they have put nitrogen. Instead of vacuum, they have put nitrogen to handle properly the sample. So once we get the sample, we can divide our priority what to do. So first is a pre-basic characterization, which can be done using a X-ray tomography. Then basic characterization using analytical balance, microscope, binocular microscope. Then few multispectral or hyperspectral scanning to get the mineral peaks using either VNR or something. Then preliminary characterization using scanning electron microscope, Raman, UV fluorescence, X-ray diffraction, X-ray, and petrologic microscope. Then after once we characterize the sample, we can go for, as earlier I talked, like a concentration measurement and isotopic study, so on. So however, it is important to understand that these until and it is not necessary, we should not do any destructive analysis. So before that, we should do all type of characteristic studies of non-destructive, like as I told, EPMA and SIMS instrument. They are non-destructive in nature. So those type of experiments should be done first instead of measurement of trace element, XRF, or in MCIC routines. So this shows just a schematic what type of analysis we can think of depending on their spot size, what should be the instrument we can choose to analyze as per our experiment design. So these are various instruments for higher, once you do the preliminary study, if you want to do further study, these are few instruments like field emission electron, ICP-MS, X-ray fluorescence, XRD, TEM, and FESM. So this also already I showed SIMS, NanoSIMS, TIMS, NCHCP-MS, novel gas. This is also one curation facility in Japan. There they can see a lot of instrument facility has been clubbed into the curation facility. Before moving the sample or distributing sample, they can use a measurement from the sample. So this is also the same.